Trying something a little bit different today with our slides. We'll see how they work out. Have a digital printout of the slides inside of OneNote, so we'll see how that works. Maybe I won't be accidentally zooming and all that all the time. Okay. So let's see. You think anything just in general we need to talk about? Okay. All right. So today's going to be a good day because we get away from that limit definition of a derivative. Derivatives are going to stick around, okay, but they're not going to be as ugly as they could be with that limit definition of a derivative. What we're going to work on today, we're going to start working on building up a toolbox of shortcuts where we can shortcut that limit definition process. We're going to work out and find some formulas and some patterns so we can find derivatives without having to do that limit definition thing. Today, the type of functions that we're going to take derivatives of, we're going to take derivatives of polynomials. So it'll take us a few minutes to build up to that, and then we're going to look at exponential functions a little bit also. And so we'll start dealing with some exponentials here. So our first goal, we want to be able to take a derivative of a polynomial without having to do the limit definition of a derivative every time. So for our starting place, let's think about a constant function. So we just have f of x equals some number. It doesn't matter what the number is. It's just the fact that we don't have a variable, we have a constant term. So I think that's probably it. So we have f of x equals some constant number. If we think about the graph, no matter what the number is, we're just going to have a horizontal line at y equals whatever our constant number is. So if we think about the slope of the tangent line to a horizontal straight line, we just got a horizontal straight line everywhere. So what's our tangent line going to look like? What's its slope going to be? We have a horizontal tangent line too, you know? So it'll be slope 0. Slope 0. Okay. So since our derivative, one way of interpreting that is it's the slope of the tangent line to our function. Then we can come up with this idea here that no, since all constant functions will be horizontal and have horizontal tangent lines everywhere, then anytime we take the derivative of a constant function, our derivative is going to be 0. Our derivative is going to be 0. So making that observation, now all of a sudden we're justified. When we see a constant function, we can just say, oh, well, the derivative of that is 0 without having to do that limit definition thing. You can do the limit definition. We can show how it works out. Okay. So the part on the left, it's our limit definition of a derivative. Here, if we're saying f of x equals c, then we would have f of x equals c plus h. So it would then minus c. Okay. But c plus h is still just some number. So what are we doing here? Let's see. Oh, no. Okay, so what do we get? Yeah, sorry. I was thinking about that wrong. So this piece. Ooh, let me change my pen size here a little bit. This piece, how are we getting that for f of x plus h? So f of x, let's see. Keep that in mind. So what would f of x plus h be? We're just getting c. How are we just getting c? Just a constant there. When does that happen? So how would we find this? We would take x plus h, and we would plug it in everywhere we had an x in our function. But what? Where do we have an x in our original function? Nowhere. Not nowhere. It's just constant. So no matter what we plug in for x, we get out c. So here, our first one, we're going to get c. And then our original function, we're going to get c. So on the top, we just get 0 over h, which is just 0. Okay, that's the long version. We don't have to do that. Okay, we don't have to do that. So one way of writing this down, this is the Leibniz notation version. As we can say, if we take the derivative of a constant, whatever the constant is, we're going to get 0. Another way of writing that same thing, then you could say, here's our constant function. If we take the derivative, we get 0. It's just a different notation. Using the little prime tick mark notation. This is the Leibniz notation. That's nice. That makes our life easy. It's a good thing, something to be happy about. Okay. So remember, we're building our way up. We're trying to get to being able to take the derivative of any polynomial. So right now, the constant part of any polynomial we can handle. Okay. But we need to be able to handle the variable parts as well. So let's think about that. So polynomials, we just have different powers of x, and then, or constant terms, and then they're put together with plus signs or minus signs. That's how we get a polynomial. So the next thing we need to think about is when we have some power of x, how do we get a derivative for that without having to use the limit definition? Okay. So here, if we start with the case where n equals 1, where we just have x to the first power, just x. Then if we think about the graph, y equals x, that's this 45-degree straight line where the x coordinates and the y coordinates match. It's a straight line, so it's going to have the same tangent line everywhere, just like our constant functions did. So our slope of our tangent line is just going to be the same as the graph, which is 1 here. All right, y equals x, so if you go up 1 over 1, you're back on the graph. So far, one way we could write that, we could say we take the derivative of x, we get 1. Or I think it's written on the next slide, but you could also do it in other notation. It is, we get so that's the first power. Yeah, there it is. They use parentheses instead of brackets. You can go through the limit definition for x squared. You can go through the limit definition for x cubed. I won't make us. Okay. How they turn out is if we take the derivative of x squared, we're going to get 2x. If we take the derivative of x cubed, we're going to get 3x squared. And then we do have an example of x to the 4th. We didn't mess with the one that bad in the last section, so let's look at it. Okay. Here we're using the limit definition for x to the 4th. Find the limit, to find the derivative. So we would have to have x plus h to the 4th minus x to the 4th. There's x plus h to the 4th. All that when we multiply it out. And then minus x to the 4th. And you cancel the x to the 4th terms. It's just a lot to have to write out, so we didn't do one that big. Cancel those out, and then you remember what we would do next? We're trying to find that limit. We would factor out an h. Factor out an h, that's what they do on the next line. So from here to here, we've lost a factor of h. Okay, so we get rid of the 0 in the bottom, and then we would plug in 0 for h. So when we do that, that term goes away, that term goes away, that term goes away. We just get 4x to the third. 4x to the third. So here's what we've developed so far. Okay. Derivative of x, 1. Derivative of x squared, 2x. Derivative of x to the third, 3x squared. Derivative of x to the fourth, 4x to the third. So somebody that hasn't learned the power rule before and you have a guess for what the derivative of x to the fifth would be. Can you find the pattern? It would be 5x to the fourth. Did you know? Do you know the power rule already? Yeah, it will be 5x to the fourth. Right? If we look at what's happening, right? Our coefficient's going up by 1 every time, and so are our exponents. So using the previous term, right? So we were at 4, so we go 5, and then we have x to the fourth. Okay. And we could keep going. And the idea is there's a pattern here. And the pattern is what we call the power rule. Okay. So here's our power rule. Is we want to take the derivative of x to some power. We make the exponent. Now we take the exponent and multiply it by the coefficient in front. It doesn't look like that's what's going on here, but you got to remember we have a 1 coefficient. So we take the exponent and multiply by the coefficient out front. So there we get n. And then our exponent's going to decrease by 1. We subtract 1 from the exponent. Subtract 1 from the exponent. And so looking at our pattern, let's go back to what we had before. Come on, slides. There we go. So let's look at the x to the third one. So we had x to the third with a 1 coefficient in front. So to get our derivative, we do 3 times the 1 coefficient, we get 3. And then our exponent was 3, we subtract 1 and get the 2. We look at x to the fourth, we had a 1 coefficient there. So 4 times the 1 coefficient, we get 4 as our new coefficient. And then 4 minus 1, we get 3 as our new exponent. So it turns out that anytime we have a power of x, we can use this pattern, and that will give us the same thing we would get if we did the limit definition to find the derivative. And luckily, it's a whole lot faster to say, well, I need to multiply once and subtract once than it is to do all the limit definition stuff. Okay? That makes our life a whole lot easier, right? So like for x to the fourth, we could either do all of this, or we could do this. Either do the limit definition, or we could say 4 times 1 is 4, 4 minus 1 is 3. And we're done. And we get the same thing both ways. So this power rule, very nice, very helpful. Makes it depressing that we were having to do them the other way. when it's that much easier to use this power rule. Okay, but we can use it now. So there's that. So our statement on this slide says from x to the n, we can find that derivative if n is a positive integer. Okay. So positive integer. We're about to expand that though. We're about to expand that, but let's look at a few more examples. I can get screen to scroll there. Yeah. So if our function's x to the 6th, and to get our derivative, we multiply the 6 out front. So 6 times 1 gives us 6. 6 minus 1 gives us the 5th power, so 6x to the 5th. And that would be our next one in the list. Right? B, we got x to the 1000th. I would not want to do the limit definition of a derivative for that one, because you would have x plus h to the 1000th, and you'd have to do x plus h times itself 1,000 times on top of that limit. Doesn't sound fun? Okay. So much easier to use the power rule here. So then y prime, the derivative of y, we'll multiply the 1,000 out front, get 1,000x, subtract 1, 999 is our exponent there. And then it doesn't matter if it's an x, just whatever our variable is that we're taking the derivative of. So here we've got t to the 4th. So dy dt, or y prime again if you want to write it that way. Multiply the 4 out front, subtract 1 from the exponent, 4t cubed. And this is just using the other notation. DDR of r to the 3rd, derivative of r to the 3rd, multiply the 3 out front, subtract 1 from the exponent, get 3r squared. So not difficult. It's really nice when you have something that's so useful and it's not hard. Power rule is a good thing. Okay. So let's look at the general version of the power rule. We can see it. We can find the pattern ourselves for any positive integer. Okay. But it turns out that if you think about other situations where maybe we have a rational exponent, so like x to the 1/3, power rule still works. Power rule still works. If you have a negative exponent, x to the negative 3rd, power rule still works. The power rule still works. We have x to the square root of 2, something irrational, power rule still works. Power rule still works. So we can expand our power rule, and we can say if we have x raised to any real number power, then we can use the power rule. That's really nice. All of a sudden we can find just a ton of different derivatives pretty easily by just using the power rule. And our textbook throws this other idea in right here. It's not a difficult concept. So we've been finding derivatives, so we're thinking about finding tangent lines to our functions. Something else that can be useful is finding something called a normal line. A lot of times when we say normal in math class, what do we mean geometrically? Well, yeah, if we're in stats, for sure, yeah, you can think about it that way. Thinking more geometry-wise, normal, we mean perpendicular. Okay, so a tangent line, right, comes almost kind of parallel to our graph in a sense. It touches our graph at one point. A normal line would go through that same point, but it would come in perpendicular to our curve. Okay? So a tangent line and a normal line at the same point are perpendicular to each other. Okay? So So maybe we've got a parabola here, right? Then our tangent line would look something like that. That would be tangent. Normal line would come in 90 degrees. So the green one would be our normal line. Okay. So, yeah. Because it makes it easy to find the tangent, right? Because when we take the derivative, it gives us a formula so we can find the slope of the tangent line at any x value. We just plug in for x, for the x coordinate of our point where we want it to be tangent. And then we could take that slope and the point where it's touching our graph and get the equation of the tangent line. So it's taking you back to algebra 1. Okay? What's the relationship between perpendicular lines? These both go through the same point. Okay? So maybe we could say we're going to go through the point 2, 4. Okay? So both of these, the tangent line will go through the point 2, 4, the normal line will go through the point 2, 4. But the slope of the tangent line, I'll call that m tan. Okay. How is that going to be related to the slope of our normal line? Remember, what's the relationship between the slope of perpendicular lines? Yeah, there. Yeah. So, all right. So parallel lines, what do we know about their slopes? They have the same slope. Perpendicular lines have opposite reciprocal slopes, and so they're inverses of each other, and then they have opposite signs. So I wrote that without thinking about what I was writing down. We would have negative 1 over the slope of the normal line. So let's think about that. We'll call our function x squared here. And now that we know the power rule, it's easy to do the tangent line, okay? Because the slope of our tangent line our formula is going to be 2x. That's our derivative, using the power rule. And if we're going to use this x value, what's the slope of our tangent line going to be at x equals 2? Just 2 times 2. So the slope of our tangent line at the point 2, 4 would be 4. So the slope of our normal line, what would it be? Got to be the opposite reciprocal, so negative 1/4. So then our normal line would be y minus 4, our y coordinate, equals negative 1/4 times x minus 2. That's our normal line. With our tangent line, we just use the other slope. The tangent lines are the ones we found last time. So it'd be y minus 4 equals 4 times x minus 2. That's our tangent line. It's our normal line. So if you have the tangent line, it's really easy to get the normal line. You just take the opposite reciprocal slope. Okay. We're just usually, at least in calculus, we're usually more concerned with the tangent line, but the normal line's not any harder. All right, so, okay. So we can find the derivative of a constant term, or a constant function. And now we can find the derivative of any real power of x. So we're really close to being able to find the derivative of a polynomial, okay, just any given polynomial. The missing pieces we have, the way we make a polynomial is we take powers of x and put them together with plus and or minus signs. Okay. So we've got a couple more rules for combining functions. Okay. Oh yeah, and we also can have coefficients on there. So here's, let me zoom out of that a little bit. Here's another useful rule. Okay. It says if we want the derivative of a constant times a function, then all we have to do is we find the derivative of the function and multiply it by whatever constant it is. So think about this. So we can find derivatives of powers of x, but what if we want the derivative of 3x? Okay. So we can handle the x part. We can handle the x part. That's what we talked about, the power rule. This constant multiple rule is telling us this is going to be the same thing as doing 3 times the derivative of x. We can move the 3 outside the derivative. And then what's the derivative of x? 1. So 3 times 1 is just 3. So the derivative of 3x is 3. Okay, so that's a useful one to keep in mind because sometimes it can be a little confusing using the power rule here just because we don't have an exponent written down. You can think about it with the power rule as well. We take the exponent and multiply it by the coefficient, so 1 times 3 will give us 3. But then it's a little weird thinking about the power rule with the x, okay, because we do 1 minus 1 and get x to the 0th. X to the 0 power is 1, so we get 3 times 1, 3. So the short way of thinking about it, and I think it's how most people think about it when you're taking these derivatives, is if you have some coefficient in front of x, that's going to be the derivative. Okay. So derivative of 7x, what would that be? 7. Yeah. So it's just whatever coefficient's in front of the x, if you just have a x to the first power. And it even works if you have weird things like we got square root of 2x. Okay. Yep, just square root of 2. Okay. Square root of 2 is just a constant, so it works just like this one. Okay. Just like this one. So let me get caught up with you here. Okay. And, okay, yeah, we've got another good example in here. Got 2 good examples, actually. Okay. So we want the derivative of 3x to the 4th. Okay. The technical way of thinking about it is that we can bring the 3 out in front of the derivative because it's a constant, and then find the derivative of x to the 4th. So using the power rule, that would be 4x to the 3rd times 3, and then get 12x to the 3rd. Okay. The way I think it typically, in practice, it typically gets thought about, and if we want the derivative of 3x to the 4th, we take the 4 and multiply it by the 3. That's what the constant multiple rule says we can do. We're just doing it in a little bit different order. And so we'll get a coefficient of 12, and then subtract 1 from the exponent to the 3rd. Okay. It's just, we're just kind of consolidating steps if we think about it that way. And then b is useful to think about. We've got the derivative of negative x. So we can think about that like having a constant factor of 1 as our coefficient in front of the x. So we bring the minus 1 out. We've already said the derivative of x is just 1, so we get negative 1. Get negative 1. And again, the shortcut way of thinking about that is like we have a coefficient of negative 1 in front of the x. So if we take the derivative of something with just an x, it's just going to be the coefficient. So negative 1. That's the same way we thought about that last one. Okay. All right, so a couple more pieces here. What if we want the derivative of one function plus another function? Luckily, that works out really easy. All we have to do is we find the derivative of the first function, the derivative of the second function, and then we can add those together. And so if you have a plus sign between two functions, you can split them up. You can split them up. You can just find the derivative of the first piece plus the derivative of the second piece. Okay, so that makes life easy. Okay. And you can extend that idea to any number, any finite number of functions. So like if we have 3 functions added together and we want the derivative, then you can just think about the first piece and using our property twice. Okay. But we end up, any finite number of functions that we want to add together, we can split them up and find the derivative separately. Okay. And then we can do the same thing with subtraction. Okay. We want the derivative of the difference of two functions, split them up. The derivative of the first one minus the derivative of the second one. So if we take all these rules and put them together, now we can find the derivative of polynomials. Any polynomial we come across, we can find this derivative without having to use the limit definition. We're just doing a little bit of arithmetic, and all of a sudden we have a derivative. So that's really nice to be able to take a calculus idea of finding a derivative and simplifying it down to 5th grade level math. Because all we have to be able to do is multiply, divide, add, and subtract. And really, we don't even have to be able to divide sometimes. So these are not bad. Okay, so let's do a few. Okay, put that idea on pause. We'll come back and talk about exponential functions. Where's my button here? Whoop. Let me get us some scratch paper. Okay, so let's work with some polynomials. Let's see. All right, so here's a polynomial. So let's find the derivative. We'll look at the first term. Multiply the exponent by the coefficient in front. So 7 times 2 is 14. And then what do we do next? Subtract 1 from 7. Yeah, so we get x to the 6th. Okay. And then we can find the derivative of the next term. So 3 times the negative 1 that's in front there will give us minus 3. And x squared. Yeah, and the last one's 0, so it's plus 0, so we don't have to write that down. That's it. Okay. And I don't want to think about how long that would take to do with the limit definition, okay, because we would have to do x plus h to the 7th power minus x plus h to the 3rd power, okay, and then cancel out all those things that cancel, and then factor out an h from all of that. Okay, so a lot better. Because it's constant, so if you take the derivative of a constant, you get 0. It goes away. Right? Look at another one. Here's something a little weird. There's x to the 2/3. So if we're going to find the derivative, what we'll do, we take the exponent, we still just use the power rule. We take the exponent, multiply it by the coefficient out front, so we had a 1, so 2/3 times 1 is 2/3. And then, how do we get our new exponent? We subtract 1. Okay. So, yeah, so we've got to get a common denominator, right? So it'd be 2/3 minus 3/3. So we get negative 1/3. And if we wanted to get rid of the negative exponent, sometimes it'll be useful to do that. Sometimes we won't care about having the negative exponents. But if we wanted to get rid of the negative exponent, it would be 2/3 x to the 1/3. Go down into the bottom. Okay. So sometimes we'll just leave it the first way. Sometimes we'll move it down. Okay. The arithmetic can get a little bit trickier. When we have fractional exponents sometimes, so like so there's some nasty function. We want the derivative of that thing. We do have to work on our fraction arithmetic a little bit. So that'll be important. So there we would do 7/5 times 7. So what would we get there? Yeah, so yeah, 7 times 7 would give us 49, and then 5 times 1, or just know the denominator is going to be 5. And then if we subtract 1 from the exponent, it'd be 2/5. Yeah, because our version of 1 we would use would be 5/5. So we get 2/5. Well, it'll be on the next one. It'll be on the next one. Yeah. That rule's nice. Okay, let's look at a couple other situations you'll come across. So we got one like this. We have 3/x to the 5th, so something over x to a power. Right now, that can look a little confusing the way it's written. But we can find this derivative pretty easily still. We just need to do a little rearranging. Ideally, we would have our variable just out to the side of our 3. Yeah, so that's kind of the opposite of maybe what you're used to doing in algebra class. Right? We say get rid of all the negative exponents. But in this case, we actually prefer to have it in the negative exponent form, because we take this thing and move it up to the top, we'll have 3x to the negative 5th. So now if we want the derivative, we can just use a power rule. Like we had before, we have to be careful with the signs. But negative 5 times 3 would give us negative 15. And then here we have to be careful with the signs. We'll have negative 5 minus 1. So we'll get negative 6. Negative 6. And then if we had a good reason to get rid of the negative exponent, we could. It would be negative 15 over x to the 6. So it's not obvious to look at it in 3 over x to the 5th form and just see right away the derivative is going to be negative 15 over x to the 6th. You can kind of see how they're related, but so it can be useful if you have a variable in the denominator to move it up to the top by making the exponent negative. Look at another one. This one's a little interesting. Because the way it's written, we don't have a rule for it yet. So this is, alternatively, this is x plus 1 times x plus 1. So you had to be a little careful. Unfortunately, we cannot just find the derivative of the first one and the derivative of the second one and multiply them together. That was not on our list of options. Okay? The operations we can do that with are plus and minus. But we don't have a rule yet for multiplying two functions. How do we take the derivative there? That's still to come. Okay? But this one we could find with our rules that we do have. Okay? What could we do to... Yeah, we can multiply it out. Just multiply it out. So this, you do FOIL and then combine like terms, get x squared plus 2x plus 1. And then what would our derivative be? We'd have 2x, and then the derivative of the 2x part plus 2. The derivative of the 1 part, that's constant, so it's just 0. So there's our derivative, 2x plus 2. And we'll look at this a little bit later, but again, just if we tried to take the derivative of each factor and then multiply them together, we're not going to get the right thing. Because the derivative of x plus 1 is just 1. And then the derivative of x plus 1 is 1. So if we did 1 times 1, we would get 1, which is clearly not 2x plus 2. Not 2x plus 2. So sadly, not going to be quite that easy with a product. We'll get there. Okay. So, feel free to do algebraic manipulation on whatever you're working with. Okay. The power rule still holds up, even if you have weird numbers. Okay. The sum and difference rules and the constant multiple rule, they all still hold up, even if the numbers are weird and ugly. you can use those. So, task number 2. Let's our derivative of polynomials there. Task number 2, we want to talk about exponential functions. Or we need to talk about them. You might not want to talk about them. We need to talk about them. So we want to talk about exponential functions and then their derivatives. So bear with me a little bit as we walk through this. So let's try to remember a little bit about exponential functions. So here's some exponential function we're calling b to the x power. So if we think about trying to do the limit definition, okay, when we plug into the limit definition where we get b to the x plus h power, now plugging in x plus h to the exponent, minus b to the x. Okay. You can use the exponent rules of exponentials here, that if we usually use it the other way around, that if we're multiplying two terms, we add the exponents. You can use that in reverse. Okay, get b to the x times b to the h is the same thing as b to the x plus h. And then there we get a constant factor, or we get a factor of b to the x that we can factor out. Okay. So we take a look. Okay. B to the x does not have an h in it. So b to the x is not going to change no matter what value we use for h. So in that sense, it makes b to the x a constant term here. So we can pull that constant factor of b to the x out in front of our limit, and we get this thing down at the bottom. Okay. We get that the derivative of b to the x is b to the x times this limit. The limit as h approaches 0 is b to the h minus 1 over h. The thing that's really super interesting about that, okay, is comparing or noticing that we started with a function of b to the x, okay, and then when we look at the derivative, it's got a factor of b to the x in there. Okay. So when we take the limit of an exponential function, it's going to be it's going to come in as a multiple of itself. A multiple of itself. So also, okay, remember that, let's look at this, okay? It says, notice that the limit is the value of the derivative of f at 0. Okay, why? Why is that true? Here, let's think about f prime at 0. Okay, that would mean we're going to plug in 0 for x, right, in that limit definition. So let's back up. So here, let me show you where I'm looking. Here, we'll plug in 0 for x. What are we going to get? We'll get, so we'll get b h, right? 0 plus h is just h. And then if we have b to the 0th, what are we going to get? Remember that? Anything raised to the 0th power? 1 over h. So that's what that slide's saying. Okay? It's saying that this limit that we end up with, b to the h minus 1 over h, that's the same thing as f prime of 0. Okay. So another way of writing our derivative is to say that f prime of b to the x is f prime of 0 times b to the x. So that's pretty interesting if you stop and think about it. So the derivative of an exponential function is going to be a multiple of itself, b to x, and not just any multiple of itself. It's going to be a multiple of itself that is whatever the value of its own derivative is at 0. And so it's going to be a f prime of 0 multiple of itself. And that's true for any exponential function. Any exponential. So that's pretty weird that it works out that way. Let's think about that for a couple of values for b. Okay, so here we're thinking about b being 2, so 2 to the x is our function. 2 to the x is our function. So then f prime of 0, this limit, okay, would be about 0.69. Okay, so the derivative of 2 to the x, I don't think they spell that out real well here. The derivative of 2 to the x, we said it's going to be f prime of 0 times itself. So it's going to be approximately, we'll estimate here, okay, approximately f prime of 0 when b is 2 is about 0.69 times 2 to the x. So that's weird. That's weird. We just get this number from somewhere times itself. Okay. And you can get more precise. So if we change b to 3, the f prime of 0 value changes. Okay. That one comes out to a little bit over 1, about 1.10. Okay. So we could say the derivative of 3 to the x is about 1.10 times 3 to the x. Okay. So the thing that our textbook is about to make a big deal about, and it's rightfully so, okay? If we look at these f prime of 0 numbers, for 2, we get about 0.069. For 3, we get about 1.10. So can you think of a really important number that's somewhere between about 0.69 and about 1.10? There's one number that's really nice to work with that's somewhere between those two. 1. So it turns out, thinking about what exponential function would give you 1 for f prime at 0 is a really important question. Really important question. Okay. And if we make these comparisons, a b of 2 gives us 0.69, about a b of 3 gives us about 1.10. So the base, the b value, that would give us f prime of 0 equals 1 should be somewhere between 2 and 3. Should be somewhere between 2 and 3. You know any famous numbers that are somewhere between 2 and 3? We got? Yeah, okay. I mean like really famous. E, yeah. So pi might come to mind. Pi is a really famous number. Oh, it's too big. Pi's too big. Because 3 is too big. But yeah, there's another really famous number. Okay. That's between there. And that's when we deal with E. So that's one way to define the number e. Okay? Is we could define the number e as the number that when we take e to the x, that this limit, or f prime at 0, is 1. That's one definition for the number e. Okay? E pops up all over the place in math. Okay? So e actually has a bunch of equivalent definitions. That's one place it pops up, though. Okay? That's one way it pops up. So what does that mean? So remember, that is if f of x is e to the x, then this limit is f prime of 0. So what does that make f prime of x? We saw on the last one there's going to be some multiple of itself, and the multiple it's going to be is f prime of 0. So what's f prime of 0 here? 1. That's how we got the e. So something really remarkable. Might not seem all that impressive on the surface, but it is. That we just figured out a differentiation rule. If our function's e to the x, what's our derivative going to be? E to the x. Okay. So in words, right, this thing says it more technically. It says you can define e such that it's the number that the limit of as h approaches 0 of e to the h minus 1 over h equals 1. Okay, that's great, nice and technical. We can use that. But in words, another way of defining e is a number such that if you raise it to the x power, it's its own derivative. E to the x prime, the derivative of e to the x, is e to the x. So, and let's think a little bit more deeply into that. Remember, one interpretation of the derivative is it's the rate of change of the function. So another way of thinking about this is that the rate of change of e to the x is proportional to itself. Right? It's the function. You could say it this way too. E to the x is the function so that its rate of change is itself. That's weird. The good thing for us right now doing computations is finding the derivative of e to the x is really easy. So what's the derivative of e to the x? E to the x. E to the x. Arguably one of the easiest derivatives to find. It's just itself. So there's graphs. So there's our rule. Okay. Yeah, and there's another way of saying the same thing. Okay, that if you think about the slope of the tangent line to the curve e to the x, it's going to be the same thing as the function value. Okay. That's another interesting way of thinking about it. All right, so let's look at this thing. So it says if f of x equals e to the x minus x, find f prime, and then find something we haven't mentioned yet. And compare the graphs. Let's just think about finding the derivative first, f prime. Okay, so the difference rule says we can split these up. So we just need the derivative of e to the x. We said that's itself, e to the x. And then the derivative of negative x, negative 1. There's our derivative. This thing with 2 tick marks, okay, is called the second derivative of f. It's not bad. All we're doing to get a second derivative is we take the derivative of the derivative. And we just take the derivative again. So when you take the derivative of a function, you get another function that we call the derivative. And we can take the derivative of the derivative to get the second derivative. Okay. So some notation here. Okay. We could take the derivative again and get the third derivative. Or we could take the derivative again. Usually after 3, the way you notate that with the prime notation is you would have parentheses with the 4 and get the fourth derivative. There's no limit to how many times you can take the derivative, because every time you take the derivative of a function, you get another function, so just take the derivative of that function. And in theory, it goes on and on forever. You could never get to the bottom of that rabbit hole. And the general notation, we can talk about the nth derivative. Our textbook has already covered these, but I didn't get into it yet because when it was finding second derivatives, it was using the limit definition. If you use the limit definition, you have to go through that process twice to get the second derivative. And I spared you that. It's much easier to use the power rule or something to talk about higher order derivatives, is what you could refer to. So real quick side note. Okay. Here's f of x. Right. Okay. Here's a function plus the derivative of that function. You're just using the power rule, so yep, 7x to the 6th plus 5x to the 4th. So if we want the second derivative, we just take the derivative of the derivative. Yeah, 6 times 7 will be 42, x to the 5th plus 20x to the 3rd, yeah. Yeah, we could keep going, yeah. The numbers might get a little big depending on what your coefficients are. So that's 2, 10, x to the 4th plus 60x squared. Okay. And you can keep going. One thing to take note of, though, and I kind of picked one that was a little too big to use, so let's just do it. Let's start with something with a smaller exponent out here. There's a function. Our derivative would be 2x. Our second derivative, what would it be? 2. Our third derivative would be 0. What about our fourth derivative? It would be 0. So at some point, when you have any polynomial, your whatever order derivative will turn into 0, and any derivative after that will be 0. That's true with polynomials. The one we started with would do that too. This term would be 120x on the fourth derivative. On the fifth derivative, it would be 120. On the sixth derivative, it would be 0. So at some point, okay, yes, in theory, you can take as many derivatives as you want to. Okay, but at some point, who cares anymore? I mean, because the third derivative is exactly the same as the nth derivative on this one. And that's true at some point for any polynomial. Okay, so somewhere in there, and it differs depending on what we're working with, but somewhere in there, it's not useful anymore. But we do find use for it in situations. Okay, almost there. Let's see. Let's do maybe like one more example, and then I'll let you. Okay. This Friday. So look at this function. So there's some nightmare. No, it's really not that bad, but there's some unusual looking function, at least written on paper. It's not a nice normal polynomial that we deal with. But we can find the derivative. We've got everything we need to find the derivative of that thing. We maybe have a little bit of work to do ahead of time. On the second term. So square root of x, we can rewrite that as an exponent. Yeah, so right now, yeah, if we leave it in the bottom, it'd be 1/2, and then we can move it up to the top. So that we'd have 8x to the negative 1/2. So having to do a little algebraic manipulation there, but now we just use the power rule. And our derivative of e to the x rule. So here's what we're working with. So what's our derivative? 7 e to the x is a little weird. But remember, 7 is just a constant, so we've got that constant multiple rule. We can just worry about the constant at the end. So the derivative of e to the x is, yeah, e to the x, and the derivative of e to the x is e to the x, and then times 7, so 7 e to the x. So look at that, e to the x, even if you have a coefficient in front of it, it just stays. And then use our power rule on the other piece. We've got negative 1/2 times 8. That's negative 8 over 2. Be negative 4. Yeah, so be careful with the signs on these. We got to subtract 1 from the exponent. So getting a common denominator, that'll be minus 2 over 2. That'll be minus 3 over 2. And then let me see what WebAssign makes you do. WebAssign will let you leave it like that, which is good. Okay. If we run into the situation where we need to get rid of the negative exponent and put it back in radical form, we would have minus 4 over x to the 3/2, right? And then we change that back to radical form. So then that would be square root of x to the 3rd. So WebAssign's okay with this. It's okay with that. Okay. Which is good. I was stressing a little bit thinking WebAssign was going to make us get rid of negative exponents every time. So. All right. Okie dokie. Y'all go have a good weekend. If you didn't get on the sign-in sheet, it's up here. Have fun watching the Super Bowl if you're into that.